wrong meeting. Wouldn't want to start a public hearing, no. That. All right, so we call to order, this is an information meeting. I'd like to, next step is to approve the agenda.
So moved.
We got a motion, second, all in favor? Aye.
Aye.
So this is an information meeting. Next on the agenda, oh, you have it up there and I'm looking on here. Is the update from about our charter from Mark Peterson.
All right. Well, good morning, committee members, and welcome to the Water Resource Committee meeting. And we do have an unusual action item today. We do have to approve updates to the charter. So while this committee is primarily an educational and information committee, we do have to do that. So a couple things before we get started. I think we have some really interesting stuff for you today. And again, kind of as a reminder, we started this committee several years ago. I guess it was 2020, I think it was. And really with the idea that with the CIP and finance committees, those are where all of the items that need board approval come through. And there's a lot of activities today, you know, a couple of really good examples, primarily some really, you know, interesting stuff that goes on in our planning department that is work that's way out in front, stuff that's kind of behind the scenes, stuff that isn't come to you and you get to see because it doesn't come for board approval. And so this is an opportunity to share some of that and really get behind the scenes on some interesting stuff. So we're excited to go through that today, but first we will do, and we also have besides that, we have a great update on the lead pipe program and the process there and some good stuff there. And at the end, I'll finish up with a little recap and look ahead to some potential topics for next year. But first, let's go ahead and back in September with the finance and CIP committees, those charters were updated. We have to do this every three years or so. So we do need to take care of this item. It's in board docs. You've probably seen it. Really, we aren't recommending any changes. It still kind of captures the essence of what the committee is and the purpose. There was a little cleanup on some staff contact information. So, you know, unless there are any other questions about it, I think we can probably move forward with this. And I think the charters for the CIP and finance we'll move this forward to next week's board meeting, and you can choose if you want to put it on consent.
So the two board members, you've seen the changes in blue. You're okay with those?
Yep.
I suggest, and we now have the correct spelling of Jules' name. We need a motion to approve it and put it on consent.
Second.
All in favor?
Aye.
And let's put it on consent.
Very good.
The information items, we're going to start with the data modeling. I'm excited to hear this one.
So if you haven't met me, I'm Darren Gelder. Excuse me, I manage our planning program and among other things. And we're going to talk a little bit about kind of what goes on behind the scenes and some of the tools we have, and then how it all plays out, how we actually use some of that as we move ahead. So the planning program overall, you've seen me recently present the capital improvement plan. That's one of our major tasks that we help organize every year. We are also, especially Andrew Beatty, who's not here in the room, is really our primary contact with the county's water wastewater program. And he's been working with them for years, does a great job. And then the other really big thing that we always tackle in planning is master planning, and that could be for the whole system or for like area facility plans, smaller plans within our region. So we've done a lot of planning recently related to the JLMA, and over the next year or so, you're going to see a number of master plans where we're going to step back and look at the whole system, make sure everything's integrated together, And that'll be for water, for wastewater, and for reclaimed, separate projects, but related. And we'll be bringing those forward as we move ahead. And each of those master plans is going to include some projection work, which we're actually underway with, models, which we'll talk a lot about today, how we use those models in developing scenarios and alternatives, and then how that leads kind of to capital planning. So the process of master planning is kind of, hasn't changed for a long time. We start with the data we have or that we know. We put that into some sort of model or projection, and then we will do the analysis on that. And so today, I really want to talk a bit about the data, the modeling, and then the analysis that we do, not really the whole planning process. And we're really going to focus in on the water distribution system planning. We could talk about reclaimed, which is very similar. Sewer gets a little different because it's all gravity, but the water distribution system is one of the keys that we work on, mainly because that's one of our key public health and safety issues. We need to maintain pressure. We need to maintain fire flow. We need to maintain demand capacity under current and future conditions. And so we try and make sure that we do that reliably, making sure that we have the redundancy in our system so that everything is networked. There's multiple paths to get water to a location. And then we're always looking for alternatives that help with cost. We want to make sure that whatever we put in the ground is right sized for now and for the future. We don't have to come back in a couple of years and build it again. It's very expensive. So, but our work is partially that, looking out to the future, but it's also day to day. It's kind of fun because we get to work on operational issues like helping our development team coordinate sizing and locations, reviewing fire flows. We also look a lot at like maintenance outages or outages related to new construction and how might that impact our system? Are there any concerns we're going to have with when we can actually do the construction or meeting the demands that we have? And then we're one of the kind of few teams at Loud and Water that's really charged with looking way out into the future too, and looking out 20, 30 years and trying to think, well, what do we need to help support our whole system, whether that's the permits, the capital program, or developing those projections that lots of our teams use. And because of that, we're also one of the teams that really has a lot of regional outreach. We wind up talking to our neighbors a lot and trying to understand what's going on, not just here, but in the region. So it's a great mix of kind of daily stuff and the future. And so we'll dig in a little bit to kind of the data that we use, which I love, and we have such great stuff here, the tools we have, and then the kind of how we put it in action. So I'm going to start with the data side. And this is all basically in-house stuff that we're doing. We'll start at the top. The SCADA system is our sensors, essentially. And those, we have literally thousands of them, mostly in the plants, but also we have almost 200 of them out in the distribution system, measuring pressures, flows, tank levels, pump performance, all sorts of aspects of that. We also have our AMI system, or our metering system, which is collecting hourly usage information from about 85,000 meters in our system. It's a lot of data, to process. And then our GIS system, which is really a kind of our system of record of all of our infrastructure. And that is critical to when we're building the model, so we know not just the pipe length, but the size, the diameter, the age, the material, all that stuff is buried in our GIS. And so the teams we have here in-house that build all this stuff are tremendous. And previously I worked in consulting. Not everyone's nearly as good as Loud and Water. And then in the past couple of years too, we've also been, sure.
Is there an easy way to tell if my meter is one of the ones that are looked at?
So if you're in Loudoun County, every meter is monitored. Every meter is AMI now. Everyone is something we could look up if we could dig in, find your meter and look up exactly
Not
what
that
your
I'm planning
hourly
to do
use
anything
is.
untoward, I just curious.
No,
they-
no, we can't.
But there's a
Um,
good side to that. So
Yep.
when my toilet was running, I got a note that water flow never stopped. You might want to check something at your house. It's
Mhm.
that system that
Yep.
did that for me. Saved me a lot of money.
Yeah. No, we have a lot of built-in quality control tools or analysis tools in that metering system so that if we have use that seems out of the ordinary, we can flag it and check it and see and perhaps find a leak before people would notice it. So yes,
My neighbor had that happen.
yep. Um,
Oh, yeah.
And then in the past couple of years too, in-house, we've been developing a ton of data visualization tools, mostly with Power BI. These are a couple examples of kind of, we can look year over year at the growth in the system in different types of flows. But we also have financial dashboards and work order dashboards, all sorts of things that they have been building for us that give us it's really great to visualize what the data is. Looking at the numbers, it's sometimes hard to see.
What is this built on?
Power BI, it's a Microsoft
No, in Microsoft.
tool.
Okay.
There are a few other visualization tools out there, but it's a great way to organize the data. It's once you have kind of the background built, it moves along pretty quick. There's a lot of options.
It pulls the financial data from our
Yep, SAP.
SAP system. Yeah.
So we have, the finances are directly pulled from SAP, as our GIS data, metering data, all sorts of things are now tied through this.
Pretty sophisticated.
And it's been a great indicator for us. But today I'm going to talk mostly about the water modeling that we do. And I like to say it's mostly just lights and camera angles, so it's not that hard. But we do lots of different types of models in-house here that we manage. Our water distribution and reclaim distribution systems, we have all pipes, hydraulic models built for those. The wastewater collection system, we have currently a large pipe model. It's not every pipe. Wastewater is a little different than water because it's basically not networked the same way. And then we also have a raw water supply model that we're still kind of in the early stages of, that Pam will talk about a little bit later. So we'll really dig into kind of this all pipes model, the distribution models, because those are our key tools that we use. And we take advantage of this model in a lot of different departments, a lot of different ways. We use it a lot for, I'll just highlight a couple, the operations, looking at outage planning, and we'll talk more about that in a few minutes. And then, of course, we use it for master planning when we're looking at growth and developing the capital improvement plans. So the modeling is basically helping us organize the data. It's a little philosophical slide maybe, but it helps us organize the data so that we can make sense of it and we can use it more properly. And we also recognize, though, models are never precisely correct. When we have 85,000 different demands, different meters every day, changing all the time, there's always something that's not going to be exactly what's in the model, but they're pretty close and they're very useful for us. So the model itself, it's based on really known physics, known energy equations. In one pipe, it's very easy to figure out what's happening with the water. But when you build a network of pipes, it gets very confusing because there's so many options for the water to move. But basically, it's a lot of energy equations, and we lose energy in the pipes as the water moves through and there's friction and as it turns different directions and so on. So we have to figure all this out. If you want to parallel kind of to what our network looks like, you can make a lot of parallels to transportation or driving. Most of you, if you had to go to the airport after this, you might pull up your map on your phone or in your car, and you kind of know where you're going to go there. But it would tell you if there's any blockages or outages. It's very easy to use this, but there's a lot of parallels. If you went there, you'd probably go on the biggest roads that carry the most traffic. And so in the water system, you can kind of think of, if I talk about the modeling, the roads are kind of like pipes. They're very networked. There's lots of different ways to get to the same location. The intersections are kind of like nodes or junctions would be the words that I would maybe using later. Stoplights are kind of like valves. We can change the direction or stop flow if we have to. And the cars kind of move like water, and the destinations are the demands. So a destination like the airport has a large demand. A destination like your house probably only gets a few cars a day. It would be a small demand. So we'll go dig into a couple questions and kind of talk about how we actually used it here. So we have kind of an operations question, which is what happens when a facility shuts down? What are the impacts? Do we need to be careful for any reason? And then kind of a capital or development question, how do we serve a new area? So I'm gonna back up and just talk a little bit about the whole system and kind of dig down, narrow it down to the system or the part of the system we're gonna talk about. So this is a map of our whole central service area. You can see there's 3 big arrows there, which represent essentially 3 sources to our system. Now, the 2 on the east side are both Fairfax, but we have 2 major connections to the Fairfax water system. And then we have our trap rock supply up in the west. You also notice there are a few different colored shadings there. We have different pressure zones or different kind of energy levels in our water system. As we move up into the higher levels, higher elevations, we have to push the water up there. So we give it more energy, we push it up into those higher zones. And then the other things you see on there are kind of where our storage tanks are, and that's also generally where our pump stations are, so we can store water to help buffer demands. Interconnecting all this is our highways or freeways, our major pipes. And then within that system, we have the smaller network of kind of distribution level pipes. So we kind of split it up between transmission, distribution, and there's actually a whole bunch more pipes on here that you don't really see in this map, but they're all kind of shown here in green. So this is, you're kind of looking at the same thing again. We have the 2 sources, or the 3 sources, the roads, the facilities, and we can take the model and we can actually then watch how the water moves through the model to perhaps trace if there's some quality concern. If we're going to shut down a system, we can look at how that water is moving to figure out how it's impacting that. So we're going to focus in on this 600 zone, the green shaded area. And if you look just at that green shaded area, it also kind of has its own sources. So it has 2 pump stations that are pumping the water from the lower energy zone up into the higher, up into our 600 zone. And then we also have a storage tank, which to help meet our peak demand, that's going to drain some and help supply water to that system. So you can kind of think of, we have 3 basic sources. And just a little more background, in that system, it's almost 5,000 meters in that zone. They're almost all residential, which means the usage is very similar. And we also have a lot of usage out there in particular that's large lot residential. There's a lot of irrigation. So what happens with a lot of irrigation, especially in the summer, we see a very big early morning peak. And this is one of the things we can do with our AMI system, is we can basically sum up all those meters in that zone and see how are they actually using water hour by hour. So this is a 24-hour period. This is one day, July 8th this year. And that zone used almost 4 million gallons of water for that one day. It's a pretty high use, and you can see a tremendous peak in the morning, over 600,000 gallons of water in 1 hour, or about 10,000 gallons a minute. To supply that much water, we need all 3 of those sources. We need both pump stations, we need the tank. This is getting close to the limits of what we can supply to that zone. If you trigger your memory, you'll remember we're actually doing some upgrades in that zone right now. We're doing the Dulles South pump station upgrade. Brambleton, I think, came through too as a study, and we're doing some construction out there too for some transmission mains. So if we're going to look at this, we may think about, can we shut something down during this period? And we know it's no. So we think, okay, a lot of times our capital team will tell them, no, we need to do it later in the year. So if we look later in the year, you'll see in October, again, similar peak, but about half as much demand. A big early morning peak. It's still pretty high actually for October. And this would be kind of questionable if we want to shut anything down at this period. So we thought, okay, let's push it out a little bit farther. And if you actually look down in November, demands have dropped again. We're down to about 1 million gallons a day. And that peak is now down to maybe 70,000 gallons in an hour instead of 600,000 gallons in an hour. So the peak is almost 10 times less. It's a tremendous change, especially out in that zone. So that zone's been a bit of a challenge as it's grown because those morning peaks are kind of off the charts, bigger than the rest of our system. So anyway, we looked at this and said, okay, we should probably do this construction more in November rather than July, obviously. So we actually then said, okay, this is our Dulles South pump station. We knew we actually had to shut it down. We're adding a new pump out there. So our questions were basically, can we meet demand and will we maintain pressure? The operators, our distribution system operators who have great intuition were a little bit concerned about this one because they knew the station gets stressed, especially in the summer. So if we look in at that zone, you can see where we are. We're going to focus in just on the southern part of that zone because the shutdown to our facility is that southern pump station. So if we kind of zoom in on that, this is what the model actually looks like. So I've added the arrow there to say that Dulles South pump station is going to be out of service. And we can see all the pipes are in there. And we also have dots there or nodes. Those are our junctions. And one of the things the model allows us to do is to color code that to say, and we can set this however we want to look at pressures. So currently that's indicating that we have a lot of blue dots, relatively very high pressure kind of actually in the 80 to 120 range. And then a lot of green dots, which is in 40 to 80. That's perfect. That's what we want. We want our system to be in that range. That allows all your household fixtures, everything to work. So this is actually the model run at that higher demand. We tested it at that just to say, could we actually do it? And it's a good example for a session like this. So at 2 a.m., if you remember, there wasn't that much demand. We can meet demand even without that pump station there. So we have no supply coming in from the south. All of it's coming from the tank and the northern pump station. It works. At 4 a.m., pretty much the same. It's still relatively low demand. We're good. At 6 a.m., it all failed basically. So without that supply at that high peak demand, we can't meet demand. And this is if we started seeing these red pressures under 20 PSI, that's a regulatory issue. That's a health safety issue. This would cause us to have to issue boil water notices. It's really not something we want. If the pressure in the pipe gets too low, then we risk having water leak into the pipes. We never want that. If we have any leaks on our pipes, we want it to leak out. If it's leaking in, then we're getting contamination. But it is curious though, by 8 a.m., the system largely recovered. So we know that, we're close to meeting that demand, not quite. And we have improvements actually planned that should make us actually work without that pump station soon. So even though we modeled it, we did all this, we actually did the shutdown. We did the shutdown around, I think, right at the end of October. And so the other thing our AMI or our meters do, some of them, not all of them, a few of them have pressure sensors built into them, and we can monitor the pressure out in the system. So we went back and said, okay, let's do a little forensics. Did this work the way we thought it would? And we went back in and looked at one of the meters in that southern zone there, in that area, and said, well, what are the pressures? And you can see that the pressures, they vary every day. That's totally normal. They're varying here maybe 3 PSI normally up and down. If no one would ever notice that in their system. It's very small, it's very consistent. And then you can see on the last day there, we did actually do the shutdown and pressures dropped a little bit, but hardly at all. So it was, a successful shutdown. They got the work done that they wanted to get done. We make them pre-plan, obviously, so they were only shut down for a couple hours, but they were able to pull out the pipe, cap it off, and get everything back in service. And now they're working on installing the next pump. So this was a successful shutdown. It really helped us use the model to kind of predict, and then we went back and said, did it actually work? So when we look at a zone like this, we'll look at all sorts of things. We'll track tank levels. Tank levels are a good indicator for us of, is the system behaving properly? We want the tank levels to go up and down every day so we can move water in and out, keep it fresh for all of us. And so we can use this all sorts of ways. And we could have color-coded the pipes to show velocities or show other indicators of our system. So I'll move on unless you have any questions.
It's quite impressive.
It's fun to use. It obviously takes a lot of work to maintain it too. As we change settings, and our operators are great, but they like to change things and make sure it's working the best. So we'll move on and do kind of a very different application here and look at capital development kind of, and how do we serve a new area. So if you remember the 600 zone, we kind of had a known sources, we had a storage tank, and not all the pipes are shown there, but the major pipes are shown on here. And you can see we have a whole network of pipes. We have a backbone. If there's new development there, we can basically just add on a small piece to our existing system. If you flip now and look out at the growth area out toward the JLMA, and this really includes some of the westernmost parts of our central service system, we kind of know, excuse me, that there's a source there by Trap Rock. We have some big pipes. We also know there's a large pipe that runs up and down Belmont Ridge Road, but our network out there is non-existent. We don't have anything out there. We don't have any water pipes, any sewer pipes. We have no facilities. So if we're looking at growth out there, it's all a question mark right now. So we'll kind of walk through this general steps we take to look at this kind of system or any parts of our system and help review it. And these methods would also apply even to new or existing areas where we're perhaps seeing a change in our land use or zoning that's allowed, or a lot of redevelopment. So this scope we kind of develop of how to look at all this, and this is standard planning again. We kind of take the data, we look at the demand, the flow projections, we'll update our models, make sure all those demands are in the right place in the model, and then we'll run the model to look at different scenarios and alternatives. How do we serve this area? And we're going to look mostly in the model at kind of that peak day. Can we meet the pressures? Can we meet fire flows? And can we kind of keep velocities down low enough so we aren't risking ourselves, risking our pipes? Sometimes when you talk about velocity, we talk about it in terms of hydraulic gradient, in terms of how much loss, how much energy we're losing in our system. So then we'll lay it all out and come up with a plan. And then we also always think of some other like sensitivity analysis or other scenarios that we may need to kind of think about, keep in the back of our mind. We knew when JLMA first came, first thought was, we're going to be close to the town of Leesburg. Do we need to make another connection? Do we not? We talked with them, we talked to the county. At this point, we're not making a connection, although there's still some perhaps discussions there. We're thinking about water quality. We don't want lots of huge pipes with dead ends that just sit there for years and never get used. So we're always thinking about that. And of course, just the demand and flow projections are variable.
Are you able to use the model for water quality, the model itself?
So I would say no. we use the model for water quality in one way. We can look at water age. The model will help us determine how long the water is in the system before it gets used. So if we start at a source, it takes 4 days to actually get to a meter and get used. So we can look at water age, which is a great surrogate, a great indicator of water
Yeah.
quality. But it's not exactly like chlorine decay or how our disinfectant decays in our system, because that's highly dependent on temperature, on the actual pipe conditions, on all sorts of factors. It makes it a lot trickier. The other thing we do in our system now is we add chlorination, we add disinfectant at a number of our storage tanks. So we have multiple sources for disinfection, which also makes the modeling of that very tricky. So we haven't used it as a exact water quality model, but the age is a great surrogate, and we've used that with our compliance team to help set up where we want to have sampling locations, where we need to do testing. So yeah, I thought about that, but the cost and the benefit of that just don't seem to pan out for us. So this is kind of the same map I showed you before, but we're going to go a little bit more to kind of a sketch here, a little bit more of the cartoon version. Again, you can kind of see the major roadways going through there. The dark blue on the map there is our existing pipes, our existing infrastructure. And the green is the sewer. We won't talk so much about that today, but that's actually was probably perhaps more challenging than the water because of the topography. And we like to use gravity on sewer, and we can't use gravity everywhere there. So we have these blue major facilities. And the next thing we looked at, of course, was kind of, well, what's the land use out there? What might our demands grow to, or how would we potentially serve this? So right off the bat, we kind of roughly mapped out, what are these areas? What are we serving? There were some areas that are designated essentially residential, or maybe some small commercial. Those are in the kind of dark green. And then there was a number of areas that were more industrial, commercial, which for this area basically means data centers. And those are kind of in that purplish color. Bowen Park kind of sits in the middle there, and then you can see the quarries are also mixed in there. So we looked right away. We already knew, actually, town of Leesburg already serves Bowen Park. We wouldn't be serving that. There's a couple other small areas in this map that we knew we wouldn't be serving. The part that's marked JLMA West, that's kind of by the Leesburg Airport, that's the Microsoft parcel that's been in the news a lot recently, and the town is actually annexing, or did annex. That was a big question mark for us at first, because we really didn't know what was going to happen there. And the other thing that was tricky about all this is the data centers, because if they all came in as water-cooled data centers, that's a lot of demand. If they come in as a mix of water and air-cooled, it's less demand. If they all happen to be air-cooled, it would be a lot less demand. So it was a very tricky proposition at first to say, what are the demands out here? What can we meet? The other thing we looked at quickly was the elevations. Do we need to actually push the water up even higher and build a new zone? Luckily, all this area is compatible with our existing zones. It's easily served with our current energy levels. So we took this system here and we kind of said, okay, when we first start, we're kind of just sketching. And we say, let's kind of follow the roads and put in some major infrastructure. Where might that go? And so we kind of laid out a quick backbone of larger pipes that would serve all these areas. And then we also start to think, okay, what are the interconnections, the smaller networks that we need to serve this? And this all starts really rough and really, kind of back of the envelope, but it gives us a good feel for what might come out there and what kind of sizing we're looking at. And then we'll spread demands throughout the system based on the land use or based on developments that we've already heard about. in this area, there were a lot of developments almost ready to go. So we kind of had an inkling as to what was coming. We knew that there were going to be 1,000 homes up in the kind of toward the JLMA West, up in that transition policy area. So we had some ideas of what was coming. So we spread all these demands out. We put them out in the zone, and then we started basically sizing pipes. What size pipes might we need? And we came up with a whole series of proposed pipe diameters. And then, and some of this is based on our kind of rules of thumb. This might be a little hard to see, but there's pipes mixed in there along with different boundaries. And this was one of our very first early versions of this. It's changed significantly since then. But we would review this, and we're going to look at those key factors. One, what are our max day demand? Can we keep pressures up even under max day demand? Regulatory goals are above 20 PSI, but for this level of planning early on, we want to make sure we have at least 40 PSI everywhere. Gives us a little conservative approach, a little bit of a buffer there or contingency. And you can see in this map, if you look at the numbers that are typed in near some of those dots, and it's also color coded, all the pressures are basically in that 50, 60 range. Some get a little bit higher, but this is great minimum pressures at that peak hour demand. We also looked at the max pressures, just curious as to how high might they get it to serve this area. There are a few areas up there near the low elevations of the creek that get pretty high, but they're reasonable. We can deal with that. We have a few parts of our system wherever it gets really low elevation where we have some high pressures, and so our teams are used to that, and we can design around that. We'll also look at our basically velocities, and this was measured here as kind of the hydraulic gradient, but this helps us tell which pipes are getting used or which pipes are close maybe to the sizing that's as high as we want. And the kind of dark blue pipe near coming out of trap down at the south there, we know that's about at its limit. We might almost want to upsize that one. And we actually have some parallel pipes in there now, and then we'll also look at fire flows. Can we meet industrial level fire flow and maintain pressure? And basically this said, yes, with this size pipes, with the demands we assumed, everything works. So we were happy with this general layout. We've continued to refine this and change this quite a bit as we included some of the new demands in our Western service area, and as we tied it all together. And then we also, one of the tools we have in-house, we have lots of great mapping here. So we actually added to our system maps that we use inside here some kind of really general proposed alignments of major pipes. And those are the dashed lines on there. And that helps our land development teams, helps our planning teams kind of know something's proposed here. It doesn't have to be exactly in that location, but we need to kind of get from A to B. And so this gives our team knowledge so they can help negotiate easements or get the pipe sizing that we need. And we have those actually scattered throughout our whole system. So that's kind of the look at the new part of our system. But of course, we also tended to look at, well, what happens to our existing system? If we add all this demand out here, do we impact how our tanks change, how our tanks turn over? Because that's one of our key indicators of, are we meeting our demand? Are we keeping up with things? So we did that, and we looked at kind of our central system. And what you're looking at here, it's a little bit hard to read that, but those lines on the graph are basically tank levels. So the tank levels go up and down multiple times through this 3-hour extended simulation. And we can run this over time. We can watch the tank levels go up and down. That's exactly what we want. We don't want them to get too empty. They all stay more than 50% full. That's kind of a rough guide, not a rule. And then they go up and down, meaning we're moving water in and out, keeping the water quality fresh. It helps everything. So that's our existing system, no new demands, things are working. So our existing system, we added in the new demands. We made just a few operational changes. We didn't play with the existing system too much. And you can see things definitely changed. We are stressing the system a little bit differently. But at the end of the day, what we want, what you kind of look at is every 24 hours, do those tanks recover? Do they get back to the level kind of where they started at? And they do. So we see them drain, we see them refill. It's a different pattern, but it still works for us. A couple of the tanks are getting down near that 50% levels, so it's something to watch. But even with all that new demand, and this was kind of built out in the JLMA, millions of gallons of new demand, it still worked. So we were happy with that. It kind of shows the level of redundancy and contingency that's been built into our system through a lot of planning that came even long before me. But then, of course, we didn't just look at today's system. We tried to look out in the future. And we said, okay, with future demands, what's going to happen? And we didn't change our existing infrastructure at all. We just added a bunch of demand. So you can see in this system, without the JLMA, even before that, we knew that one of the tanks, that's our 600 zone tank, actually starts to empty a little bit more. That would indicate, hey, we need to do something out in that zone to help improve supply. That tank is now being stressed a bit to meet that peak day supply. So we're actually doing those things with the Dulles South upgrade and so on that we just talked about. And we also added in the JLMA and looked out in the future and we say, oh, yeah, another tank's getting stressed here. We're getting it down below 50%. That's a problem. But this is also 20 years in the future. So this gives us that indication, okay, this is going to be one of our capital projects. We need to look at how to improve this. We also need to monitor, do those demands actually develop the way we think they might develop? Because those demands, everything always changes. The data centers get bigger, but they get more efficient, but their peaks stay high. So we keep on watching that. As the development moves in, we don't, sometimes land use changes, density changes, and every once in a while our boundary changes, which is even more tricky. But that gives us time and it gives us an indication that, hey, we need to do something to help improve this. And this is what we'll be going through in the master planning process, looking out in the future and trying to make sure that we're ready for that. So those are kind of the tools we use. So just as a planning program, some of the next steps that you'll see from us, and we'll be back in front of various committees over the next few months, talking about master planning, perhaps sharing some of the projection work that we've been doing. We'll be talking about model updates and just actually developing that whole new master planning for water system, for the wastewater, for the reclaimed. We actually were here already once for the reclaim, well, not with the CIP committee, for the wastewater system, because we started some flow metering and model development on that project. And this should all lead to, with those new tools and visualization that we have, better communication, better visualization of what we have, what we know, so we can share it with our capital teams, with our asset management teams, with land development, with everybody. And then if you want to just talk kind of the future of modeling and the future of what's out there, there's a lot of tools that are out there that are proposed and that the vendors want you to buy. A lot of it has to do with integrating SCADA data directly into your model to perhaps building a real-time model or a model that's very much up to date that could give you better decision-making for day-to-day operations, make a better tool of it. Sometimes called a digital twin. We've looked at that. It's a big lift to get there, and we're not sure it gives us the benefits right now. It may come. And then we're also kind of watching, there's a lot of vendors using AI or machine learning tools to, one, help manage the data, because there's a lot of data behind all this. And there could be some QA/QC or just insights that we gather that way. The one way we have used it a little bit is kind of optimizing results. When you think back to how I talked about looking at those pipes, and we looked at the pressure, we looked at the fire flow, we looked at the velocities, and that was for one set of pipes, one set of demands. And then we got to do it again for one different pipe size, or one different demand scenario, or one different tank setting, it can quickly multiply into dozens, hundreds of scenarios that take a lot of time to process. There are now some optimization tools out there that help basically run the model 1,000 times and give you a kind of a chart of here's some of your best options. That's something we've looked into a little bit, and perhaps we'll be using it again as we move forward. But that's kind of some of the future of what we're looking at there. And then we're also looking at, I'd really like to share the model more with other people. Internally, our land development team uses it for development review. But I think our operators could also use it some to help look at the system. And as we go through this master planning process, part of that is also going to be developing a few basic modeling scenarios that will work for them, that we can let them use and help understand some of that too.
You use this modeling in your disaster planning?
Yep.
In that recent exercise, were you using this, the one with the multiple water companies in the area?
So we do some of that. We have looked at a number of different like disaster planning, basically source outages, and how we could deal with that. The model allows us to look at kind of criticality of facilities. So we can take any one facility or multiple out of service and see what are those impacts. What level of demand maybe could we meet even if we didn't have
The Potomac.
the Potomac? Yeah. Without the Potomac,
We don't have much.
we don't have much. Nobody has anything really. Most systems in the DC region are in trouble.
Yep.
But we also then, kind of when you start looking at the Potomac, then, Pam's going to talk about that because we are starting to look more at our options with the Potomac, and especially with Milestone Reservoir coming online in the next couple of years. That will give us different options.
Yep. Be interesting to see some of those projected models. Yeah.
Yeah.
I'll let Pam.
Yeah, Pam can go on that one. Sure.
You check fire flows.
Mhm.
Do you assume it's just one hydrant or there's an area flow, or how do you do that?
So the fire flow, there's a fire flow tool within the model, which helps us tremendously. But basically, we're looking at the flow at one hydrant at a time. But we're usually looking at, like, for example, in a commercial area, we're looking, can the system deliver up to 3,000 gallons per minute? We know actually one individual hydrant will not deliver 3,000 gallons per minute.
No.
That it's usually a 6-inch pipe to the hydrant. You're not going to get that much out of it. You might get 2,000 maybe, but even that's a stretch. So we know that any one location is going to probably take multiple hydrants. So we're really kind of looking at the system and not an individual hydrant. Can the system supply 3,000 gallons
Just
per minute to this area or to this kind of vicinity?
But around a school,
Yeah.
high school,
Mhm,
they would, the fire department, if there was a fire,
mhm.
they would use multiple hydrants.
Right. Yep.
The reason for that model.
Yeah. So we know in reality, yes, the fire department is going to come in there. They're going to use all the hydrants they got and everything in the area. And they're going to probably pull 3,000 gallons per minute from our system. It just won't be one individual point. So yes, we do review that, and we look at then not just, is there enough flow and pressure at that node, but everywhere back in our system. Because perhaps you could have a huge flow over here and you're going to drain your neighbor up the hill or drain the tank. And so the model actually allows us to look at the pressures everywhere for the demands in one location.
So the 3,500 is for industrial, is it?
Yeah.
Do you do the same thing for subdivision?
Yeah,
Same amount?
every different type of development area has different fire flow requirements. Subdivisions in our area basically require 1,750 gallons per minute. General commercials like 2,000, townhomes are, I think, 2,000. Some commercials 2,500, most industrials 3,000. So it varies through the area. We generally test things first, always at 3,000, and just assume the worst case. because even in a residential area, sometimes you get schools or other churches or other buildings that might have a slightly higher demand, fire flow demand. So it's rare that we have only residential areas. So we generally test it higher. We know there's a few areas that are lower.
A question about urban planning areas. You know, the
Mhm.
comp plan 2019
Yep.
has put a lot of emphasis on the urban planning areas where
Mm-hmm.
we don't yet have much development, but we're
Yep.
getting ready for
Yep.
hopefully more intense development. How are we looking at that? We're modeling that.
So we did do some kind of like area facility planning or looked at what are the potential change in demands that we had projected for that area. So we do that two different ways, kind of. We lean on the county because the county develops population and employment projections for very small areas, traffic analysis zones. So we lean on them because they develop those, and that's a great known number that we can reference. So we look at what's potential, and we have added that in different scenarios to try and see how might that impact us, or does it really change what we already have there? Most of those urban planning zones that they pick near the metro, we've kind of known they've been around for a while, and we already have a pretty good backbone of infrastructure that's more or less in the middle of our system. So we aren't too concerned about it, but we did look at it. And I think it will be interesting to look at the master planning, go back and look at the whole, because there have been changes to the land use, the urban planning areas. We've got the Dulles Western Lands, which was a new area for us to serve actually, and it's all data centers. There's the JLMA areas. There's a little kind of Red Hill Road area there with the school and stuff that wasn't originally part of our service area. So yes, there's always those.
It's going to be more creep like.
Yeah, and I know, I mean, the county at one point had talked about buying that parcel out, I don't know, 300 acres out by the transition policy area up kind of toward Leesburg up there. Then they backed out of it, but we're kind of wondering, who knows, it might come back. And if that's more schools or more other things, that may change some of the plans too. So we're always trying to maintain a little bit of a contingency. And we always kind of look at that sensitivity. Can we supply unknown demands or new demands in an area that we don't really expect without actually saying, hey, we're planning to expand out to Percival or whatever. That we aren't going to look at that. That's something we don't want to touch.
Darren, Mr. Allen has a question.
Sure.
Hey, Darren.
Hi.
You just brought up my question when you mentioned Percival. So I know you don't want to touch that, but when you model for expansion into the JMLA, how much thought goes into sizing the pipe under the assumption that at some point we would have to go west of Evergreen Mills Road or, even further west than that? Is that possibility, even though that could be 20, 30 years in the future? Is that possibility contemplated when you start sizing pipe into the JMLA?
I would say generally no, but we do always include a buffer or some contingency level, sizing in everything we do. When you looked at what we did up there, we're planning to loop everything, but we also want to make sure we could actually supply any of those areas without that loop. So each individual area is strong enough so the loop makes it even stronger. So we know we probably have, we hope we have more capacity out there than we probably need at this point. So we could expand somewhat, but really we can't start, I don't know, at least for me, I feel we can't really start spending a lot of energy or money to oversize our infrastructure today for what might happen. So we have contingencies. We do make things maybe large enough to provide a safety margin for us and provide some buffer should there be an unknown, but not particularly out there. The one directly we really looked at was just the town of Leesburg. And if we added 2 or 3 million gallons a day to help supply them, would that change pipe sizes, basically?
Darren, I have a couple of things to add, and they may answer a little bit of maybe Mr. Allen's question and maybe Mr. Vega's. In terms of serving some new demand out west, we do think about like corridors, as we're sizing the new piping. If we had to extend something further west, maybe we've already kind of at least built into that the thinking of where a larger line would at least be able to be headed in that direction. But as Darren mentioned, we have to be a little bit careful. We don't want to put in big pipes into the system and put them in now, kind of headed in that direction, because if the demand never comes, and then you start creating potential water quality issues because you have a lot of water sitting out there that doesn't get used. So there's kind of a balance. So I would agree with Darren where he says, no, generally we don't plan for that, but there's a little bit of thinking that goes into it. Again, maybe just trying to think of how might we sort of extend one of our existing transmission mains that maybe isn't quite extended out that far yet, but what might that corridor be? So that was one thought. And then maybe Mr. Vega, to the question about the urban development areas, when we do this modeling, we have very limited normalized pipe diameters that we use. So in theory, the demands may actually require a 14.2 inch diameter pipe to serve them. Well, we use a 20-inch pipe as that next diameter. So it builds in all of this additional capacity because you're trying to use these commercially available standardized pipes. And then when we also do some of our failure analysis, we'll look at, okay, the system said, the math said we needed a 14.2 inch pipe. We put in a 20. And now for a redundancy standpoint, we're going to let's break that 20 and assume that 20 is out of service. It may tell us that if that's the case, then this 16 over here needs to be upsized to a 24, and we'll plan for that. So now you're building all this additional capacity in the piping system. So in some ways you could say it's kind of over-designed to meet these projected demands, but that gives you that great buffering that in the future, all of a sudden, you now add 2,000 more homes. Chances are that capacity has already kind of been planned for. You just maybe now decreasing a little bit of increasing the risk that you're willing to take on because you're eating into a little bit of that buffer that you already kind of previously designed. So that's all built into the planning that we do. So I don't know, that's why maybe unless you have a really, really big redevelopment that's really significant, and as Darren mentioned, we already have pretty big pipes in some of those areas. It's not likely to have a big impact on us, but we always remodel it and look at it. And in the future, maybe we will have to add another pipe or take a pipe out of the ground and increase its diameter and size. So
I think what's unique about the urban planning areas in Loudoun is that they are greenfield development, and we're planning completely in greenfield. We're not redeveloping. We got a blank canvas of 400-foot long city blocks. So it's whether we make the whole network 12-inch pipe just to have complete redundancy for every block in the urban planning area. So it's.
Well, and you're right on. There are times we make decisions like that just say for uniformity, let's put these all in as 12-inch or maybe add a couple more 16s where in reality, again, the math might say they need to be 11.7 inches or something, right? So, yeah.
Let's not buy custom pipe. No, that's very good. Are there any other questions? Any other questions online? So I want to thank you very much. It was a
Very
great
interesting.
presentation. I really like the slides too. I mean, they're there. Could you announce which board members are online? I meant to do that at the beginning.
Yes, Mr. Allen is joined online.
And Mr. Allen's the only one?
Yes.
They're going to miss this. I'm glad this is being recorded. So thank you, Pam. I think you're up next.
Yes, and this is something that we're really excited to discuss with you. This one is a tool, Oasis, And we're going to talk a little bit about how we envision using it and why we selected it and the origins, frankly, of the tool. This OASIS, I'll call it decision support tool, is a model, but it's a mass balance model. And so it operates differently from what Darren was talking about with our hydraulic models. They work on conservation of energy. This one is really more arithmetic. Mass balance, what comes in, balances with what goes out. This tool was originally developed back in the late 80s for the ICPRB, and it supported different cooperative exercises on the Potomac River. And so that is really the basis of it. Is it has all of these regional assets. You see the whole Potomac Basin here with all of the reservoir assets. And so somewhere after, I think into the 90s, the ICPRB developed another tool called PRISM, and that's their preferred tool, but they still maintain this original OASIS tool, which provides us an opportunity for doing some cooperative modeling if we get to that point in the future. Overall, OASIS actually was developed by a firm called Hydrologics, and then they were acquired and merged with Hazen maybe 5 years ago. And since its lifespan, this model has been used pretty extensively across the country in some interesting applications. River basins have utilized the models. States have used it for state level water supply planning, hydropower applications, hydropower negotiations in particular, and then all types of collaborative decision making because you can run little tabletop exercises with the model. Some of the things that we're probably going to be most interested in it for are looking at climate change. We've been exploring how climate change might impact the resource and the availability of supply. And tied to that is drought management, capacity, like Darren's been talking about, the capacity of our facilities. We also expect that we'll be using it for a lot of operational support. So in order to utilize this, we took the ICPRB model and we populated it with all of our assets that are key to the raw water supply. So that's raw water intakes, raw water reservoirs, the treatment facilities, Broad Run, because Broad Run is a factor in our permit for our water withdrawal, and then our Fairfax water purchase, because that also balances out the demands that we have in our system. Currently, Fairfax Water provides about 60% of the demand to our system, and we use Trap Rock for 40%. And that, Darren's talked a little bit about indicators for water quality, and that provides, we've found that to provide good water quality in our system. And so that's kind of an operational rule that we intend to carry on. I think the key with this is that operational rules. This model is built up to, it connects points, and you can see by the arrows, it shows the direction of flow. But really, it's about operational rules that we put in place and we test the system. So there's 3 different configurations that we can utilize this model for decision making. We can use it for planning, and that creates trends similar to what we were seeing on the finished water side. Reservoir storage, we can look at reservoir storage fluctuation based on demands in the system. We can also utilize the model for operational purposes. We can look at what's the probability of, low flow in 90 days based on the today. And the way that we can do that is because this model actually is pulling in databases that are much bigger than Loudon Water. We're pulling in data from USGS river gauges, we're pulling in NOAA data. So basically, we're grabbing onto some of those larger scale, basin scale databases, and that enables us to look at percentile probabilities, which is a really interesting application that we can do with this model. And then from an exercise perspective, you can run, it's called a gaming mode, but you can run exercises and say, okay, this is the probability. These are the different, streams that might happen based on today. Well, what if the flow drops in October, and you can run different what if simulation type exercises, and you integrate your planning team with your operations team. So really, we wanted to give you far less detail, frankly, than Darren. I don't have exciting graphics to show you today. I just wanted to get you excited that we have this tool that we're going to be using for planning, operational support, as well as permit compliance. Yield is important to us. We had in 2014, Loudon Water acquired all the Goose Creek Beaver Dam assets and the water plant. And then in 2018, we brought Trap Rock online, and now we're projected to have Milestone on in 2028. So we keep adding complexity to our system, but that's also reliability and redundancy. And so something like this model provides us that ability to determine what is the best use of the different assets. So, yield, utilization of those reservoirs. We've currently been using it based on flow prediction of what types of turbidity impacts we might be experiencing at the Potomac intake. And so it's been a useful tool for the water operations team, even in the short term for that. And then permit compliance. We can take these demands that we've been talking about for the distribution model, and we'll look at them rolled up. We look at time steps more like days here, not hours. And so you're really looking at permit compliance, daily permit, weekly permit compliance, the annual permit compliance. We'll be able to take these numbers and run, what ifs and how we might best work the assets together. Yeah.
I'm just curious, turbidity impact, how do you work with that? How do you predict turbidity impact?
Excellent question. It's an indicator. So what we know is that some of the USGS flow gauges also have water quality. And so the major ones, we go look at the ones upstream and go up into West Virginia, right? So we can track the big points coming down the river. And so we can watch the wave, if you will, of flow. So there's a high flow event upstream, and we can see the turbidity that's being experienced there, or TSS. And then we'll kind of track it as it's coming down. And we've determined over the last couple of years that we've been, playing with this, we can determine which is the best gauge for us to look at and know that it'll be here in a day or 2 days. And so that gives operations the heads up.
So they will know if they're going to have to let it settle in the tanks longer.
Right,
With the higher turbidity.
right.
So that information is very useful.
That's right.
Yeah.
So we can turn down the intake and depending upon the duration of that flow event, maybe we could let it pass, or perhaps we just, modify our operations somewhat and rely more on Fairfax water supply.
That's useful for chemical spills also. So
Absolutely.
Okay.
Absolutely. But it's all,
Let's not talk about that.
but, well, if that happened, we would be relying on ICPRB because they have actually developed a really interesting spill model. And so they're even trying to take their 2-dimensional model and turn it into a 3-dimensional model. So they are really actively, for the benefit of the region, working on something that's far more sophisticated.
So how did this work with that spill of several years ago? That was the very light oil that was on the surface, the turbine oil? Machine oil.
I think the sheen is particularly challenging because that's the 2-dimensional nature is their model can't discern the difference between in the water column. right? So you have the sheen on the surface, but yet it's not mixed. It's not well mixed. And so when you deal with a simpler model, you have to make assumptions about something being well mixed. And so that was challenging. The model doesn't really, the model can, you can tweak the model, right? And if there's a slug of something that starts upstream and you can measure how the concentration might change as it's moving, you might be able to draw some relationships. But it's not, it isn't, the current model isn't developed to look at things that are on the surface.
So we're one of the few intakes on the river that is on the base of the river, is on the bottom intake. Well, most of the others are on the surface.
So Fairfax Water built that intake in the middle of the river on the bottom.
But Fairfax did one also, that's right.
Yep.
Yeah.
But then they found that because of the sediments, the fines, that just rivers are always moving. They were getting tremendous amount of sand, basically in the intake. So they learned to operate based on flow conditions, whether they were going to take water from the middle of the river or whether they were going to take it from the onshore intake. So they actually have the capability to use both. WCC has one on the shore, and they too wanted to build one in the middle of the river so they could get the benefits of higher velocities going through the middle of the river, whereas on the shore, you tend to get, the algae, the leaves, and even some of the, high sediment flows will hug the bank. So the desire for them was to move in the area intake, also build, like Fairfax, have a secondary intake in the river, not to get more capacity, but to provide the opportunity to switch back and forth. But it was very expensive, and they tabled it, frankly. They had to spend a lot of money on some other upgrades at the Potomac plant. So they don't have it either. Really, right now, it's Fairfax Water has options. Because we have Fairfax Water, we have options too.
But I think what
Yeah.
you can see is
Yes.
moving forward as we get closer to the quarry, to Milestone Reservoir coming on. That's why this is so about, the more
Yeah.
data we have, the more we're going to be able to find the best, optimize the back and forth, turn the intake off and use route, the water from the quarry, from the reservoir. So that's where this tool just becomes more and more valuable as it's moving forward.
Yeah,
Yeah.
and the goose, and
Yep.
as a third dike, per se,
Right.
the reservoir. Yeah.
And that's one of the key things we are aiming to do. So right now, we're in the middle of developing a modeling plan. And our modeling plan is looking at, operational needs. Some of these needs in the shorter term, we will have to renew our permit. So we want to look at, the runs to help us kind of work through that. And then we are going to have a workshop soon to see what other needs others might have, and kind of create a catalog of runs. And there's a lot of, Darren showed you a teaser of Power BI, some of the charts that are available to us. We've been developing the same thing for drought operations, for trap rock. And that's been valuable for them. So we have great potential, frankly. And I think that once things get further along, we'll be able to give you a good demonstration of different scenarios that this model will assist us with.
As we're building a more resilient system, how are we keeping track of where our sources of water, like before 2014, or there's 100% Fairfax, now it's 60. What are our projections going forward?
Well, we're looking at that you want to talk a little bit about the
On a more
demand
macro scale.
projections?
So finally,
Before you answer, we invested heavily in the Coblis plant. A lot of Loudon Water money is in there, and a very strong relationship. So it's not like we're just a vendor. They're just a vendor.
Correct.
Yeah, I mean, that's part of our projections, actually, to look at, one, all of our demands, and then also how do we best meet those? Some of that is with the distribution system. Maybe it makes sense for us to push more out of trap or out of that part of our system. Just because our demands are near there and it makes sense to use that. But we're also, I think we'll be looking at that percentage, and we know, at least right now, the plan would be, we plan to expand trap and move it up to 30 and perhaps 40 MGD or beyond, I don't know. We don't have any definite plans now to expand capacity with Corvallis or with Fairfax. That's, of course, always a potential possibility. But we know in the past that, the board made that decision, we're going to move toward trap, and I think for us, it's a great decision because it gives us that Western supply. And now we're seeing a ton of demand out there too. So it really helps our system operations to have that.
But one quick thing, I mean, historically, we were never 100% on Fairfax water because we had the Goose Creek supply from what was the city of Fairfax at the time. So historically, the only single feed we ever had was up through the first 20 or 30 years from the city of Fairfax. Once we had Fairfax water, we've always had that source from both sides of the system, which has been great. And so we've been, that's the way we've been used to operate. It's now optimizing the balance of it, that is what all of this planning is doing.
And on the southern tip of we do purchase some water from Fairfax on the southern tip.
Yeah, we have.
Do we have
At Route 50, or I mean Route 50, we have a major connection, and
Okay.
that's where we
Yeah.
that's where we get it from.
And
yeah.
then there's the connection.
And there's a connection up kind of near Route 7.
Route 7, yeah.
But both are coming from Corvallis.
Most are coming
Both
from,
from-
the other
yeah.
one doesn't come from Occoquan,
Mm-mm.
not pumped up at
No.
all.
Yeah, no, that's actually one challenge Fairfax has, is that they can't push water from Occoquan's plant, the Griffith plant, up this far north.
Oh.
They don't have the infrastructure
They
in
don't have the
place.
infrastructure in place for that. So if the Potomac was out of service for whatever reason, the northern part of Fairfax's system would be in trouble, just like us today. They could supply a portion of their system, but not all of it with the Griffith plant.
So we have a fairly large pipe all the way into the center of their system, all the way into the city of Fairfax.
Mhm.
So we have that pipe. Interesting. We've never used it, but it's interesting future.
So the city of Fairfax pipe, that transmission main, essentially when the city sold that to us, they only sold us the part that's in Loudoun County.
Yeah.
So then Fairfax Water owns the part from the Fairfax County line into the city of
Along
Fairfax.
the O&D trail.
Along the O&D trail,
Okay.
yes.
Mhm.
And they are
But
using,
it's still exists. They're using it.
they're using parts of it at
Uh-huh.
least. I don't know if they're using all of it
It's
yet.
interesting.
But yes.
Okay. Thank you. Any other questions?
Mhm.
So I'm Jessica Dezar, and this morning I'm going to provide you all with an update on our compliance with the lead and copper rule revisions. The Water Resources Committee has heard from me a couple of times already. I first presented information about this rule in 2022, again in 2023, and most recently, we had a CIP project that was approved by the board to get some support from CDM Smith to help us kind of race to the finish line here with this rule. So you've heard this a number of times, so this is probably the final wrap up as it relates to the lead and copper rule revisions. So just a real quick rundown of why the lead and copper rule revisions exist. So EPA put this revision out to the original lead and copper rule with a compliance date of October 16th, 2024, several years ago. The goal is to protect our children in child care facilities and schools. They are the most at risk with lead exposure. Ultimately, make sure that all lead gets out of our nation's drinking water, and empower communities throughout the U.S. with information about the effects of lead if they were to be exposed to this. So the lead and copper rule revisions apply to all water utilities nationwide, not just Loudon Water. So this was one of our things we needed to comply with. In the graphic here is just kind of a reminder. It might be a little difficult to see, but what we were really focused on this past couple of years with the lead and copper rule revisions was developing an inventory of the water service lines in our system. And different utilities have different setups, but the way Loudon Water's set up with our water service lines is from the water main to the meter or a little past the meter is owned by Loudon Water. So that was the easy part of our inventory because we are young, we have really good records. That was not a problem to get the information to prove that we didn't have lead. The more difficult part was the privately owned portion of the service line. So from after the meter to where it enters the premise or the home business, et cetera, those are records that we don't typically maintain. So not only is it private property, but even things like service line replacements, those types of permits would go through the county and not through Loudon Water. So there was a lot of information that we did not have at our disposal. So just to, I guess, cut to the chase is that our lead service line inventory is complete and we have confirmed that the entire system is not lead. And I'm going to get into the details of how we got to that determination. But so we've met the deadline. It's all been approved by VDH and we're in great shape with our lead service line inventory. So a little bit about what we started with and how we got to this point of being able to say that we don't have lead. First of all, we kind of developed our baseline of what we were looking for based on the private side of the service lines. We looked at the age of the properties. So the building code in 1978 changed to where the private side of the service lines, you could not use the lead in the service lines. And so within Loudoun County, we follow that building code and that we knew that was in place. So we were able to take the records that we had, which are really good records of, you know, where all of our customers are, essentially where all of our water serves. And we were able to cross-reference that with some data exchange with the county. So they provided us with the year the properties were built. Based on that cutoff date of 1978, we said anything built in 1979 or later, we can safely say is not lead. And if it was built in 1978 or earlier, we need to do some more investigation before we can confirm that information. So we had about 7% of our overall service lines in the system fell into this unknown category, which was about 5,700 service lines. So then we got to the point where we had to really dig into the more detailed work, and that was how do we verify those unknown service lines? What is the material? So from that 5,700-ish that we started with, about 7% of those we were able to rule out by doing additional collaboration with the county. So they do the inspections of service line replacements and they follow the building code. So if something was replaced after 1978, or 1979 or later, we were able to say, okay, this is not lead because they would not have been allowed to replace it with a lead pipe. So we were able to get those records from the county and do that desktop analysis to feed our unknown verification. So that was super helpful. And then 17% of those service lines were verified through field inspections. And so this is a collaboration of customers providing us with information and us going out to the customers to help them verify information. So we had a pretty big communication effort that took place. So we worked with our communications team and we did a number of mailers to customers that had the unknown status. And we provided them information about lead, the effects of lead, and how to locate your service line, determine what the material is, and how to report that information back to us. So that was extremely successful. For us, we were able to get quite a bit of response through that customer engagement effort. And we also sent out our staff to help with this as well. So we offered up in all circumstances, regardless of their circumstances, but mostly it went to elderly, disabled that needed some help identifying that material or getting into those smaller spaces. We would send out our water quality team to go and help them with that inspection and document that information. So a huge effort with the field inspection process. So about 17% of those unknowns were verified through eyes on, pictures, documentation, those types of field inspections. Then the other 76%, and I'm going to get into this here in the next slide, was conducted through a predictive model. So the predictive model is actually what we had the board approve the funding for back in like March, I think it was. So to get a predictive model, to have that accepted as a validation method, there's a series of questions that you have to go through, proposal process that you have to work through with VDH, meetings to talk to them about the model that you're proposing so that we get buy-in from all stages that it's a good model and it's fair and equitable and how it's put together. So we worked with CDM Smith and their software that they own, a company called Trinex, and they helped us to develop the statistical model that we used to get our predictive methodology. So it's, completely random sampling. They're looking at the density of populations and where all of the service lines that had unknown materials are, running it through a number of different check factors, looking at census tracts and just diversity, demographics, making sure that we've got everything kind of equitably placed around the county. So they put this model together. It's a software program that they use. They shared the model with VDH. VDH provided, their letter confirmation that this was an acceptable method. And what that allowed us to do was to narrow down those physical verifications that were required. So 410 physical verifications were required based on our model. But what was really great about this partnership and the approach with this proposal, which had really helped it to stand out among others when we were selecting a vendor, is they were able to propose backfilling some of those verifications with field work that we'd already done. So we had already completed 700 to 800 physical verifications through our, early on interactions with customers and our team. And they were able to work with VDH to kind of backfill some of those spaces to where we got it down to, after that model was approved, we only had to get 35 more verifications, which made life so much easier. So that was a huge win and a great success with that contract. So we were able to get all of those verifications taken care of and state with 95% confidence that our entire system is non-lead. So some of the things that I think were just really important to helping us kind of get to this point. I mentioned the communications campaign was a huge effort, working with our customers, mailings, door hangers, door knocking, phone calls. Our customer relations team became quick experts in lead and copper. They were fielding a lot of calls and helping them to get the information, providing that back to us to update our database. And scheduling all these appointments with our water quality team to go out there. It was a huge company-wide effort where pretty much all groups had some level of involvement in making sure this happened. The other thing we were really proud of was our peer utility collaboration. So early on, like 2.5 years ago or so, we set up a work group with stakeholders from each of the towns within Loudoun County. So we got a group together with each of the towns, some key members from the county as well as from LCPS, and we formed a little group. And we got together on a regular basis and we really wanted to ensure that we were all on the same page. We were communicating the same message throughout the county. We were all following similar methodology and bouncing ideas off each other. It was a great way for Loudon Water to really support the towns as they were trying to work with less resources, but also just share a lot of information back and forth, which I think just made things easier on all of us. And that was a really, really great collaboration that we had, that we were really excited to have formed. And that group just stayed consistent for over 2 years of meetings, and they're actually going to stick together. So, you know, we're kind of finished with our initial goal, which was to work on this lead service line inventory, but we really like working together. It's been a great relationship. So we've decided we're going to stay as a team and just pivot as needs change. So like we're going to be switching over to PFAS soon and just kind of changing priorities, but keeping the group together. So that's been pretty awesome, is just having that whole group together. Also really essential to our success was technology side on Loudon Water. We were so grateful to have the infrastructure set up that we do. Our GIS team put a lot of effort into this project, created us two different maps. So one serves as our database, basically, for all of our lead service line inventory, all the documentation that supports the pictures and inspection reports. Everything that we have is our internal database where we keep that updated. And they also created the customer facing database. I don't know if you've looked out on the website, but you can search your address and see what the status is of your service line, if we know your material, or how did we determine what your material is of your service line. And EPA and VDH kind of changed the requirements on what was required quite a bit over the couple of years. So we had some great support from our technology side, just in being flexible and helping us to keep adapting to that. And then finally, the grant funding was so helpful. So, you know, we had received a grant through the Bipartisan Infrastructure Law Fund, but we had to apply through VDH through their LEAP program, is what they call it. So we were really fortunate to get that funding to support. A lot of utilities were not able to get the 100% principal forgiveness. So we were really grateful for that. So that funding covered pretty much everything that it cost us to complete this effort. It covered all the printing and the mailing and the design work, and it covered the cost of our contract, staff time. It was really extremely helpful, in addition to customer credits that we were issuing for customers that helped to supply information. So the grant was fantastic. So last slide, just what's next. Because we're not lead, we have very little requirements that we need to deal with. So we're in a really, really good spot as a utility. We don't have to complete all these annual notifications to customers that have unknown status. We don't need lead service line replacement plans. Our tap sampling requirements are really going to change. We are voluntarily looking at our lead and copper sampling and how we have that distributed, just to see if there's better ways of doing it based on the data we have today. But those changes are just so minimal to us compared to what they would be, even if we had just one unknown in the system. At this point, we would have a lot more requirements to comply with, even if it wasn't lead. We just didn't know what it was. But we will be continuing to collect data. So we do recognize that some of these are assumptions based on the predictive model that we've set are non-lead, and we're going to continue to update that information. So we're not going to stop collecting data by any means. We'll continue to do that and report updates on that data to VDH each year, per the requirement. And I already mentioned the working group that we have is going to shift priorities, but we're kind of keeping the group together. And yeah, I just think it's been a really great experience. I think for all of us, it's been a good effort of everyone working together, both within Loudon Water and as a community. And I think we had the kind of the best case scenario result from this initiative. So pretty happy with that. But that's really all I have to share. It's just good news update, unless there's some questions.
No, I'm very pleased with the county work group continuing to expand its.
Yeah.
Mhm.
It's been great. Built a lot of really great relationships, so
And I
happy
think it'll
with that.
pay its dividends in the future.
Mhm.
Yes, yeah. Marty?
I have no questions.
The one that I have is always the thing. So we have high confidence. There's no lead in our system up to the service line into the house.
Correct.
After that, or to the school or to any institution, if they have an old water fountain or they have tin lead solder that someone used in their house,
Mhm.
when they put in copper pipes, which they're not supposed to be using,
Right.
it's not our responsibility. But-
Correct,
But
yeah.
do we want to still do, are we going to still do education that people need to be vigilant?
Yeah, absolutely.
Okay,
Yeah.
good to
Yeah,
hear.
we'll definitely be doing that.
And Mr. Bonfils, if I'm
Yes.
not mistaken, I think there is some sampling requirements within Loudon Water's system, schools located within our system. I do think there are some baseline lead sampling protocols that we, of course, comply with to help, put eyes on that. And I know the school system has their own internal program as well to help, really mitigate some of those risks that you're pointing out. And I just wanted to, don't want to repeat what Jessica was saying here, but I just wanted to really not let it go understated that EPA envisioned this rule as, you just complete your inventory by October of 2024. And that would just kick off the beginning of a years or decades long process of, we have all these unknowns. We need to just really kind of chip away at understanding the unknown status and eventually completing that. But this team has gone so far above and beyond to have fully verified all of these private service lines by the deadline that we were just supposed to publish the information. And so I think it's really a testament of the leadership and the best practices that we have in place inside the organization across so many departments, the record keeping, the GIS system, the ability of our field services team to get out there and support customers in verifying these. So I just wanted to say it one more time. It's really a really good news story for the organization. And I think it exemplifies the proactiveness that permeates so much of what we do here.
Thank you, yeah. It's not unusual that our team goes above and beyond their requirements. And we appreciate that. Thank you.
Well, that was the final agenda item. So,
There's one
know.
more. We have to talk about meetings for next year.
yeah,
We-
just
I have
wanted,
One
Yeah,
question.
please.
absolutely.
Go ahead.
A suggestion for a future meeting. I thought I read in the news that chloramines, which were put in to avoid the bad effects of chlorine, now they're looking at the bad effects of chloramines. And I think an update on that in a future meeting might be a good idea.
Yeah,
I think that's what I read. I couldn't believe it.
it is. And it's
Okay.
like very recent news.
Just
and
happened, yeah.
Yeah, so I think there's a lot of just questions and people starting to dig into that. But yeah, and that fits in. I think, as we look ahead to 2025 and look at the agenda for this committee, there's a number of things. And what, throughout the year and in meetings, we keep track of questions that continue to come up. We're certainly have heard, a number of questions around our reclaim program. We're doing some planning and work related to that. So we're sort of foreseeing at this point a pretty full update on a number of things with our reclaim program coming up, probably at one of these meetings. There's been some discussion around the groundwater well systems. So I think there's some, again, we're doing a lot of work, and analysis with that. And so I think there's some things there. But I think the last few years, we've been really hitting on a lot of water quality issues at this committee, notably PFAS. We'll likely have
Another one on that,
PFAS, continue to have new information and stuff to share. And I think at one of the meetings, we'll probably focus all, water quality, and we'll keep tabs on that and see what progresses with that and probably have an update on that. So those are some of the items that we're seeing. So.
The chloramines, all that discussion about fluoride.
Yes,
Well,
that's,
I mean,
that's also one that's
Truth,
just starting to come up.
hearsay, innuendo, that kind of stuff.
Yep.
Mark, Mr. Allen has a question.
Oh, sure.
Yeah, that was gonna be my question, was about, the chloramine byproducts as well as now the fluoride issue. So I don't know whether it would be beneficial for, at some point in the future, for the board members to have some talking points. So when we get questions, I know I've gotten them in the community system before, do we have chlorine in our water? Do we have fluoride in our water? So just being aware of these issues are probably going to become more prominent as we move into the new year. So just being prepared for those.
Very good. Yep. Oh,
Oh.
wow. That came from.
Crank it up.
Yeah, those are great points. And
Yes.
that is something we have stuff along those lines. So we'll work on that. That's a good point.
Thanks.
All right. So with that, I think that concludes our agenda. And there's one last thing is a motion to adjourn.
Second,
All in favor? Aye. Thank you very much. It was
that
great
was very,
presentation.
very good meeting. Thank you.
And